So first, let me thank the organizers for the invitation to speak here. I'll talk about some work in progress with Chris Kuo, who's also currently a postdoc at USC. So there's a well-known relationship, which we've seen a few times already in this workshop, between bipartite graphs in the real 2 torus and complex curves in the algebraic 2 torus. So for example, this projection of the hex grid here corresponds to the zero set of a generic ordinary quadratic polynomial. So there's various perspectives on this relationship, and what I'll try to explain in the talk is a perspective where the bipartite graph arises as the answer to a certain question about the curve, but such that that question makes sense for any subvariety of any algebraic torus, and such that when we ask it for a hypersurface, the answer is always a bipartite graph. So for example, here on the right, this is a picture of a bipartite graph that arises in this way, now from a quadratic polynomial in 3 variables. So this is a graph in the real 3 torus now. I've tried to color code it a bit to help you visualize. So the front and back faces are outlined in green because they're getting glued together. This little green dot here that I'm now covering with another green dot, that's not a vertex of the graph. That's saying that there's an edge that goes from the white vertex in the middle to the back edge, which then re-emerges down here from the front edge and then goes to the corner there, okay? So a question I'll come back to at the end that you can try to think about until then, there's a nice answer to it, is what is this graph and what does it have to do with this polynomial? But before we get there, let me just survey some background to explain what this term mirror coamoebae is going to mean here. So the mirror comes from mirror symmetry, and in this talk we're just going to need the most rudimentary form of this literal simplest example of mirror symmetry. So in general, when we talk about the mirror of an algebraic variety, we're talking about a symplectic manifold, let's say X check here, so that's a manifold with a non-degenerate 2 form, whose symplectic geometry somehow reflects the algebraic geometry of X. And a rudimentary form of this, which is what we'll almost exclusively discuss, is that there's a one-to-many correspondence between subvarieties of X and Lagrangians in the mirror X check, or more precisely, Lagrangians equipped with a local system. So here when I say a Lagrangian, that's a half-dimensional submanifold such that this symplectic form restricts to 0 on L, and then a local system is just a representation of the fundamental group of L. So basic example is if I take the algebraic torus, C star to the n, this is self-mirror. So I can think of it as a symplectic manifold, for example, by, and this is how we'll think about this, by identifying it with just the cotangent bundle to the real n torus. So cotangent bundles are the most basic examples of symplectic manifolds. And here's how this correspondence works in just the simplest example of C star itself. So if we think about what are the subvarieties of C star, well, the irreducible ones, there's 2 things you can do. You can take the whole thing, or you can pick a single point. And of course, when I pick a single point, I can, there's a choice there. And now if we go and think about, well, what are the Lagrangian submanifolds of T star S1? Well, there's a lot of them because that's a kind of floppy notion, but there's kind of 2 obvious things that come to mind. I can take a single cotangent fiber. It's the most basic example of a Lagrangian submanifold in the cotangent bundle. And such a thing is kind of, it's topologically trivial, so there's no local systems on it. And under this correspondence, that's what corresponds to the whole thing of C star. And this is one-to-many, and because this choice of point here actually doesn't matter, which more generally, if I have a Lagrangian which corresponds to some subvariety, and I flow this by a Hamiltonian isotopy, that won't change the correspondence. So there's a lot of, I at least have the flexibility of Hamiltonian isotopies on this symplectic side. On the other hand, there's another obvious thing I could do. I can just take the 0 section of the cotangent bundle. So that's a Lagrangian, which is S1 in T star S1. And now that has a fundamental group. So when I think about what are the local systems on S1, well, there's a C star choice of them because a local system is determined by a non-zero complex number, which it takes the generator to. So there's a correspondence between a choice of a point in C star and a choice of a local system on the zero section here. Yeah?
Can you see the dimensions of Z in L in some feature of L?
Yes, but it's a little subtle, of course, because obviously all L's will have the same dimension. So the answer is yes, but it's a little tricky to do that. Notice that here, a feature of this L is that it's compact, which actually that corresponds directly to the fact that this is a proper subvariety. Okay, but so this is how this correspondence works in the simplest example. And again, we're just going to be thinking about this example in powers. Any other questions? Okay.
So it works the same on C star to the n, right? It's just the obvious thing.
Now there's a lot more intermediate options. So yeah, you're right. These two, I could take all of C star to the n, that will still correspond to a cotangent fiber. And then this part, yeah, if I pick a point in C star to the n, I still have that same moduli of local systems on the zero section. Okay, so there's mirrors. Now let's talk about coamoeba, or maybe first let's talk about amoeba. Right. So if I have a subset of C star to the n, I can associate the following two objects. I can take its amoeba, A of Z, that's a subset of Rn, which is its image under the coordinate-wise norm and then logarithm. So this was the notion that was first considered by Gelfand, Kaprenov, and Zelevinsky. And then the kind of dual notion is the coamoeba. So this is a subset of T to the n, which is the image of Z under the coordinate-wise argument map. So I believe this term was coined and first considered by Passar. So you can think of these as two kind of approximations of our subset of Z. And a kind of general theme that I'll try to survey a bit here is that these in turn are kind of more combinatorial objects. They have various interesting combinatorial approximations, which then kind of transitively give us kind of combinatorial approximations of our original Z. So in the case of amoeba, this is the connection to tropical geometry. So we've already seen some pictures of amoeba in this workshop. And the thing that immediately kind of jumps out at you when you look at the pictures is that they already kind of look like pseudo-combinatorial objects. And a precise version of this, precise statement in this direction is that, say if I have a hypersurface, then I can take a suitable scaling limit of the amoeba, and I'll attain a tropical variety, which is that's a certain type of n-1 dimensional polyhedral complex, left out the word complex here, which retains the kind of coarse features of the amoeba. So I think the precise statement of this is due to Michalkin. And here's a picture of this, which I copied from a survey with Michalkin and a few other authors. So here's an amoeba, and then if we take a suitable kind of limit, it degenerates onto this combinatorial skeleton of it.
Just immediately, what if the amoeba has a hole inside?
You can, I'll have another picture, but I won't have a picture with hole, but a similar thing works. There will be tropical.
You get it cycled in the tropical curve?
Yes, yes. You have to be careful about how you're taking this limit, but yes. And a feature of this is that this projection plays well with mirror symmetry. So this kind of coordinate log map, there's a general name for this in mirror symmetry. It's an example of what's called an SYZ fibration. But the upshot is that there's a close relationship between, on the one hand, if I start with a variety, in particular hypersurface, I look at this projection in this amoeba, the mirror Lagrangian to Z will actually more or less should have approximately the same projection. That's a kind of general philosophy, which again is precise in certain kind of limits here. And a precise version of that statement is that I can choose the mirror of Z, the mirror Lagrangian to Z, so that the amoeba of the mirror Lagrangian is as close as I want to this tropical amoeba here. So this is a theorem of Jeff Hicks, kind of building on other constructions of Michalkin and Matesi. So when I look at amoebas, both for hypersurfaces and their mirrors, the answers are kind of controlled by this combinatorics of tropical varieties. Yeah.
So when you say you have a many-to-one correspondence between some varieties, Z and mirrors, how many is many? Like one parameter?
No, many is Uncountably many. It's an infinite dimensional parameter space, at least because, so I said this thing, I can take a Lagrangian and I perturb it by a Hamiltonian isotopy. That's an infinite dimensional choice. Like choose a smooth function on your Lagrangian, and then I perturb a neighborhood of your Lagrangian looks like T star of it by the Weinstein neighborhood theorem. And then I have like the graph of D of my function sitting in that neighborhood. So it's a Lagrangian is such a floppy thing, it has to be a many-to-one correspondence to match up with some complex geometric objects, which are very rigid things. There's more ambiguity than that, but that's a starting point. Okay.
Can you tell me what A of L is?
So that's my general notation for I have a subset of C star to the n. Remember, that's self-mirror, so I can still think of L as still...
Oh, it's still self.
Yeah, more precisely, it's in the dual torus, but I'm identifying them coordinate-wise. But so it's still the kind of thing that this expression A of L makes sense for. All right, any other questions?
So, I mean, if you have so much freedom in the choice of L, can you choose L to be epsilon close to anything, like the amoeba is epsilon close to anything you want, or like how?
No, good question. So yeah, the answer is no. There is content in this statement here, but yeah. And in fact, for both L and Z, a kind of important point here is that so they're projecting onto this tropical variety, and the local model for what the fibers of the projection look like can be described in kind of universal terms. So the Z projecting onto its variety, like independently of what specific example of Z or L you're looking at, you know that near sort of say a vertex of this graph or a higher dimensional example of that, the local picture for what Z and L look like is a kind of universal principle. So once you know that correspondence, that tells you that the topology of Z and L is completely determined by this tropical variety. So that's a principle which was, for example, used by great effect by Mikulkin to understand the topology of hypersurfaces in tropical terms. Other questions? All right. So there's amoebas. Let's talk a bit about coamoebas. So these have been studied a bit in the math literature, as I mentioned, by Passar and Nice especially. But they were kind of independently considered in the physics literature, and more or less, I think, around the same initial time. So in particular, there's a very influential paper of Fang, Hay, Kenaway, and Vafa. So they use the term algae for what I'm calling coamoeba. And they discovered the following phenomenon. So if you have a curve in C star squared, then at least in good cases, the coamoeba of Z retracts onto a bipartite graph for which Z arises as a spectral curve. So a graph corresponding to Z under this correspondence that we've seen a few times and alluded to previously. Maybe I'll say a little more about later. Well, I guess I could say it now. Take your graph gamma, choose some edge weightings, and take its Kasteleyn matrix, and then take the vanishing of the determinant of that matrix. That gives you a curve in C star squared, and that's the spectral curve of that graph with that edge weighting. And so here's an example of this. So here's, I have this curve defined by this Laurent polynomial here in two variables. I take its zero locus, and then here's a computer depiction of its projection via this argument map. So the projection is it's via some simulation, so it's kind of sparsely populated, but you see what it looks like, and it looks like the kind of pictures we've seen. If you take a bipartite graph, I draw its zigzag paths, and I kind of fill in the black and white regions, which is not done on the white on this part here. But imagine I fill in this region black here, that corresponds to this little region, this square here, and so on and so forth. So this is a picture of the kind of white and black regions of this of the zigzag paths of this bipartite graphs. Yeah.
How unique is the retraction? Because in general, we have spider moves that would give you graphs.
Yeah. So there's a lot of wiggle room built into this statement, and this is a physics paper. It's not. You don't open this paper and find a theorem that tells you when this works. You find some examples and some explanations of kind of why there's something here. So yeah, I think the best thing you could say is that you choose, say, the Newton polygon for your curve, and if you pick the coefficients well, you will get a picture where just you look at it and you say, gee, there's a bipartite graph in there. There's a bit more that one can say. Maybe I'm about to say some more, but I'll take another question. Yeah?
Then the spectral curve need to be harmonized. So how is it associated to any curve?
Sorry, say that again?
Isn't the spectral curve a harmonized curve?
So maybe I'm using spectral curve in a somewhat loose sense, perhaps.
It's not even a real curve.
I'm allowing complex edge weightings, yeah. Though there are nice things to say about the coamoebae in the RNA case too, but yeah. All right, so as I said, even when you don't have a nice projection, there's a good picture for why for kind of where this graph comes from that they discovered, and which was kind of generalized, again, to some extent in the physics literature. So this will be a kind of loose statement here, but this was studied subsequently by Futaki and Ueda and Franco Lee Song Vafa. And the general principle is that this generalizes to higher dimensions, where if I have a hypersurface in C star to the n, and let's say that it's the vanishing locus of some polynomial f, then again, in good cases, the coamoeba will retract onto an n-1 dimensional polyhedral complex, which again, you can kind of do some experiments with to kind of see that something like that seems reasonable. And in particular, the Futaki and Ueda really studied their mathematicians. They made some precise statements. So this is precisely true if, for example, if I take this polynomial here and I look at its coamoeba in T3, what I discover is that that retracts onto a complex, which is a union of 4 truncated octahedra. So here's, I guess some of these don't show up well on the screen, but this is supposed to be embedded in, in 2 cubes that are glued together, and there's numbers indicating the centers of these octahedra. 2 of them are explicitly pictured. So when I say truncated octahedra, I mean take an octahedron and then you chop off each of its corners. So now I have a polyhedron with, I guess, 6 square faces and then 8 hexagonal faces. So those give me a tiling of T3, and that's a picture of the coamoeba of this surface in C star cubed. And even when the projection doesn't play well, there's a package of ideas that kind of explains why this happens, and more to the point that the combinatorics of these, either this graph or this complex, are interesting and geometrically meaningful. So the place that these come from are the vanishing thimbles of this polynomial here. So specifically, or the vanishing cycle. So if I choose a critical point, so here what I've written is f, it's called w in this little picture. This is a picture of what vanishing thimble means. So here we're looking at the 0 locus of, again, my f, their w. That's some hypersurface, so here's some curve. If I look at a critical value of f, then above that critical value, I get some singular variety. And if I connect that critical value to 0, I can trace that singularity. If I follow it through, I will get a cycle in my original hypersurface. And as I trace out kind of that cycle as I move towards the critical point, that cycle pinches down to a point, and I have a disk. And so the picture of kind of what does this graph mean, what does this complex mean, is that the faces, their boundaries, so they live in the coamoeba, but they lift up to Z. And what they are exactly the vanishing cycles of this polynomial. And literally you can recover the 2 torus or the 3 torus by taking these vanishing thimbles and gluing them together. So in particular, if you want to ask about the intersections, like if you want to count the intersections of the different vanishing cycles, which is a very interesting thing to do, they're recorded by the intersection data of this complex or of this graph. Yeah.
Maybe I'm being dense, but the thimble looks like it's going in the wrong direction.
The thimble looks like it's going in the wrong direction. There's a good reason for that. There's more to say about why do you care about these intersection numbers. Part of it is because these thimbles also correspond to spheres. If I take, so in C star to the n cross C squared, I can look at the equation U times V equals F. That's actually the thing that these people want to study. And these thimbles correspond to spheres in that thing. What they really care about are the intersections of that spheres. And when you start talking about those spheres, then this picture looks natural. But anyway, that's neither here nor there.
Right. So the intersection form between the vanishing cycles is somehow interesting, right? So
That's right.
Can you read it off from the...
Yeah, exactly. Because you can, so here in the graph, the point is that like this faces a vanishing cycle, that faces a vanishing cycle. To count the intersections of the vanishing cycles, I just have to count how these faces of the graph intersect.
So exactly, you get the quiver.
Exactly. All right. So there's coamoebae of hypersurfaces. And in the case of dimension 2, there's a kind of nice special thing that happens, which is that notice that a curve in C star squared is already half-dimensional. And in a suitable sense, that curve is its own mirror Lagrangian. It's not, the curve doesn't start out Lagrangian, but it becomes so after hyperkähler rotation. But so the point is that the curve topologically already is its own mirror Lagrangian. So the coamoebae of the mirror Lagrangian then should be based the same as the coamoebae of the curve. So there's a more kind of refined thing we can say here. So let me tell you a little bit about the more refined thing. It also foreshadows where we want to go. To explain this, let me kind of enhance our discussion of mirror symmetry a little bit. So this correspondence that we've been discussing is actually a kind of tiny piece of a bigger correspondence called homological mirror symmetry. So the more precise correspondence we have is that if I give you this data of a Lagrangian and a local system, canonically associated to that is the data in our mirror X check, canonically associated to that is the data of a coherent sheaf on X. And so what we've been doing really is, when we're talking about subvarieties corresponding to some Lagrangians, I really mean that under this correspondence, the sheaf that's associated to L with its local system is the structure sheaf of our subvariety. So I can kind of embed the set of subvarieties of X into the set of coherent sheaves on X by just associating to a subvariety its structure sheaf. So really that's a kind of slightly more general kind of correspondence than what we've been describing. And so now in this case where I have a curve in C star square, let's considering the following setup. So let's say that Z is the vanishing locus of F. And so a precise statement of this kind of graph curve correspondence is I want to choose a minimal bipartite graph. So a bipartite graph in P2 that satisfies the kind of conditions that Pasha talked about yesterday, that has the same Newton polygon as F. And what I mean by that is that when I look at the zigzag paths of our graph, and I take their classes in, so those are some cycles in the 2 torus, I can take their classes in H1, which is just Z2, so I get a collection of vectors in Z2. I want those to be exactly the edges of the Newton polygon, or more precisely, the primitive edges. So if I have like an edge of length 2, so a bipartite graph that corresponds to this polygon should have 4 distinct zigzag paths, and 2 of them would have the same homology class here. So that's a general, so now it's a well-defined condition. If I have a bipartite graph, what does it mean to correspond to a particular curve or a particular Laurent polynomial? All right, so make some choice like this, and now here's a kind of more precise statement about what can we say about the mirror, the coamoeba of the mirror of this curve. And it's that it's epsilon close, I can choose it to be epsilon close to this graph. So for a generic z at least, with this fixed Newton polygon, there I can choose the mirror to z such that its coamoeba is as close as I like to this graph. And more precisely, topologically, this Lagrangian is going to be the Goncharov, the conjugate surface introduced by Goncharov and Kenyon of the graph gamma. And that's some ribbon thickening of our graphs. So in particular, if L, so this is a ribbon thickening of gamma. I'll come back to this construction actually in a little bit and review it. So I'm kind of not, I won't do that right now. But the bottom line is that L is a surface which retracts onto gamma. So to give a local system on L, that's the same as giving a local system on gamma. But I can give you a local system on gamma by just prescribing a bunch of edge weights. So now I can ask, given that I'm claiming that my, so if I fix now this Lagrangian, whose coamoeba is close to this graph, I choose an edge weighting on the graph, so I get a local system on L. I can ask what's the mirror coherent sheaf to that data, and the answer is that it's given exactly by counting perfect matchings on it. So to my edge weighting, I can form the Kasteleyn matrix, and then I take the spectral transform of that. That is the mirror sheaf. So so this Kasteleyn matrix, that's a matrix whose rows and columns correspond to the white and black vertices of gamma. The entries are given by the edge weights, or sums of edge weights with some labeling by monomials that we've seen in previous talks. That gives me a matrix-valued Laurent polynomial. So in particular, I get a map between these two. I can think of that as a map between free modules of the Laurent polynomial ring. I take its co-kernel, and now I have some module over this ring, which geometrically will look like a line bundle supported on some curve with a Newton polygon. And yeah.
For your local system, you need the edge weights and the Kasteleyn signs and the ZW. You need all 3 data.
So the statement is, the data is, if I fix the data of an edge weighting, and I fix the graph, and then kind of more or less canonically it has this Lagrangian kind of projecting onto it or near to it, and then I choose, that's some fixed discrete data, and then I choose the continuous data of an edge weighting, that is enough to define the Kasteleyn matrix and its spectral transform. And the claim is that the passage between the Kasteleyn matrix and the spectral transform is the specific instance here of this general notion of a mirror map, that you have some family of coherent sheaves parametrized by some kind of symplectic data in its mirror. So that's a kind of geometric interpretation of the spectral transform. So so this is a kind of enhanced, again, a kind of enhanced statement, version of the statement that if I take a curve and I look at its mirror and I look at its coamoeba, that coamoeba is kind of nice and combinatorial. It's close to one of these nice graphs that we're kind of used to thinking about. Right. Questions? Okay, so end of so there's the survey, and none of the details of anything that I've said are really important here. I just want to kind of convey a general picture that that's organized by this table. That when I look at different interesting subsets of C star to the n, and I look at their amoebas or coamoebas, the answers are always kind of controlled by some interesting combinatorics. The answers are nice. There's interesting stories here. And there's kind of 2 versions of the kind of subsets we could look at, because I could think of C star to the n either, as an algebraic-geometric thing, and I look at subvarieties, or maybe specifically focus on hypersurfaces, Or I could think of it as, from the mirror point of view, it's a symplectic thing, and maybe it's interesting to look at Lagrangians in it. But either way, I can ask about what are their amoebas and what are their coamoebas. So we've seen that when I ask about amoebas, I'm led to this world of combinatorics of tropical varieties. Here's a picture of, this is a quadric, I think it's a quadratic tropical surface in R3. And when I ask about coamoebas, well, the kind of general story for hypersurfaces is I get these kind of interesting polyhedral complex. I guess I should have said that, at least in this physics literature, the kind of name for these complexes was brain brick models or higher brain brick models. But I get some combinatorics of these complexes or in dimension 2 bipartite graphs. And then at least in dimension 2, those bipartite graphs are kind of also the answer about what is the mirror coamoeba of a curve look like. So regardless of the details of kind of what they look like, there's this kind of general picture here. Yeah.
So for the coamoeba, when n equals 2, taking the mirror is like taking the conjugate surface of the bipartite graph?
Basically, yeah. So the curve is all, yeah. In particular, the curve is already topologically equivalent to its conjugate, the conjugate surface of a corresponding graph.
And on the amoeba side, on the tropical side, what is this map, mirror map?
So on the amoeba side, the idea is that, again, you have to be able, it's very informally, you would want to say something like, oh, the curve, like a hypersurface and its mirror have the same amoeba, but you mean that in some kind of loose combinatorial sense, because of course, there's some choice about how the amoeba is approximated by a tropical thing. And then when I ask about the mirror, that's already some very floppy choice. So I should really mean something like, oh, given some fixed combinatorics in the base, I can choose the mirror to be kind of, to play well with that combinatorics so that it's kind of well approximated by that, by say this tropical variety. Other questions?
You're not telling us, you didn't tell us what goes in the lower
So of
right.
course, why did I set up this table? It's because the table poses a question, which is what goes there. So if I look at hypersurfaces in higher dimensions, so of course they can't have a hope of being kind of self-mirror because it doesn't have the right dimension. But I can ask about, well, what happens when I look at the mirror coamoeba of a hypersurface? Okay, so I'll answer that question. First, let me take a moment to talk more about this conjugate surface construction and to talk about it in a kind of more general way that will be relevant here. So let me fix a bipartite graph, not in the 2 torus, but actually just in some manifold of some dimension, an n manifold M. So I'm going to define a subset of M, I'll call it pi of lambda for right now, the following way. I'm going to take an epsilon neighborhood of my graph, and I'm going to smooth it. So here's, and then I'll smooth an epsilon neighborhood, and then I'll pinch it to a point in the middle of each edge. So here's a graph in a 3 manifold. And if you imagine it, forget that I did this pinching already. If I just looked at some kind of smooth tubular neighborhood here, if I literally just took the epsilon neighborhood, I'd have some corners near here. So I smooth those away so that I have a nice submanifold. And now I just take it in the middle of each edge, I just pinch it down onto a point there. So I get some subset that looks like this. Again, in whatever the dimension is, this will carve up my manifold into some white and black regions. So I look at the complement of pi of lambda. Some components will contain a black vertex, I'll call those black regions. Some components will contain a white vertex, I'll call those white regions. I'll label them as W and B. Oh, I guess, sorry. W and B are just the white and black regions. And now take a function, a smooth function on M, which is positive on the union of those regions, and it's just 0 outside of them. And now consider the following subset of the cotangent bundle of M. I take the log of F, I take its derivative, that's a 1 form. So the graph of a 1 form is a subset of the cotangent bundle. And I want to take the graph of that 1 form above the white region and union with minus the graph of that 1 form above the black region. All right, so first of all, this is, okay, so this is some subset of the cotangent, and then I take the closure of that. This is some subset of the cotangent bundle. And in fact, it's a Lagrangian submanifold, which retracts onto gamma. And it's asymptotic to something, if I look at, so T star M is non-compact. Its fibers are vector spaces, cotangent fibers. Imagine compactifying it with a sphere at infinity. Then it makes sense to have a non-compact subset of T star M, like this L, and I can look at its closure in the boundary of that compactification. That is going to be some nice submanifold here of this boundary here. So there's the point is the boundary of L is this subset of what I'm calling T infinity of M, which looks like the blue drawing here, except it's smooth. This kind of little pinch point gets resolved into a whole sphere up there. So here, if this is pi of lambda, we're in dimension 3, lambda will be some smooth surface. And it is filled by some, now Lagrangian 3 manifold inside the cotangent bundle. So of course, the point is that when we're in dimension 2, then this is a familiar construction. Then L of lambda, this is a description of this Goncharov-Kenyon conjugate surface. The fact that that surface in dimension, the fact that that surface embeds as a Lagrangian in the cotangent bundle was something we studied, again, in some other joint work with Treumann and Shende and Zaslow. I guess I should also, the theorem from the other page was with Treumann and Zaslow in a subsequent paper. But so this is some higher dimensional version of the conjugate surface and the conjugate Lagrangian. And then pi of lambda, that's a kind of high dimensional version of the zigzag paths of the graph. And then lambda is a higher dimensional version of the link associated to the graph that we've seen a few times. All right, so questions about this construction?
It's mysterious.
It's mysterious?
I don't know what else.
So,
What does it look like?
Well, another way of saying it is like everything in when you describe the conjugate Lagrangian, all of the ingredients in the definition actually just make sense in higher dimensions. Like if you say, well, instead of a ribbon thickening of my graph, take a thickening by balls of any dimension, and now in the middle of each edge, cut your thing and glue it back to itself by an orientation reversing automorphism of the ball. So definition makes sense, and it is what it is. And it will retain the feature it retracts onto the graph, which is kind of the key thing. Okay. All right, so we have this construction in our toolkit now. When did I? Okay, yeah, okay, good. Okay. All right, so now back to our picture here. Okay, so now let's assume we're specific. So what I said in the previous slide, despite the title here, makes sense even when n is 2. Now I want to assume that n is strictly greater than 2. And I want to let's fix the convex lattice polytope P, and we can study hypersurfaces associated with that. So take a Laurent polynomial with that polytope and look at its vanishing. So here's the graph on from the first slide, which again I said had something to do with you take a generic ordinary quadratic polynomial now in 3 variables. So question, raise your hands. Can anyone tell me what this graph is?
It's just 2 vertices, right?
It's just 2 vertices, but of course there's some choices I made in drawing this picture. So how did I make those choices? So I'm glad that, because I wouldn't have figured this out, so I was a little worried that everyone was going to raise their hands and I'd feel really stupid.
What do you mean? If there's just 2 vertices and it's bipartite and there's 10 edges, the graph is just trivial. It's just
Well, so the graph is trivial, but there's some choices I made about how, of course, there's topological choices in how the graph is connected to itself.
how it's embedded in the torus.
How it's embedded in the torus.
I mean, does it come from polyhedra, gluing, like, is it the dual graph of polyhedra?
So it's not quite the dual graph of a polyhedra, but it's close. It's kind of related in a very simple way to the Newton polytope.
Is it just a one skeleton of some truncated octahedron?
So let me.
Our normal family.
Here's a simpler picture of this graph. Oh. All right. So there's the Newton polytope. And here's what I do. Just pick a generic point somewhere in the interior of P. And now I look at the graph, and now I can connect that by a straight line to each lattice point in the Newton polytope. All right? I take that, and now I project it to the torus. All of these lattice points are projecting to the same place. So I wind up with this graph with 2 vertices and a number of edges, which is equal to the number of lattice points in the Newton polytope. So one thing to note here and to emphasize is that this construction specifically only makes sense because we're in dimension more than 2. If I'm in dimension 2, then unless my polytope is really small, then it doesn't matter how generically I pick x. There's going to be crossings. Like, I'm not going to have a graph. There's going to be crossings when I project to the 2 torus. So this is a specific game that only makes sense once you're in dimension at least 3. And so there's this. So the claim is that this graph is the answer to the question we posed a minute ago. So more precisely, so.
Is there an edge missing on the picture to the right between the white vertex in the middle and the top?
No, because notice this vertex, the edge that you're kind of asking about would correspond to the monomial xyz, but that monomial is of degree 3, so it's not in this picture. Okay? All right. So then the theorem is that this graph does the thing that we wanted to do. So we'll pick a generic Laurent polynomial with Newton polytope P, and now let gamma and L of gamma be the graph and Lagrangian that are given by the constructions on the last 2 slides. Again, if I have, so now I can weight, because the edges of gamma are just given by the lattice points in P, the choice of F defines an edge weighting of this graph gamma. So I just weight each edge by the coefficient of the corresponding monomial. That now defines a local system on L of gamma, and the claim is that that pair is mirror to our hypersurface Z. So in particular, because in choosing L, I could choose it to be kind of as closely approximated by the graph as I want, I could choose the mirror to have coamoebae kind of arbitrarily well approximated by this graph. And so now here's our completed picture of the combinatorics of amoeba and coamoebae of hypersurfaces and their mirrors. All right, I'm actually a little bit early, but I'll stop there.